Greek geometry requires absolute perfection to function. A theorem about a circle relies on a line with zero width, curving perfectly around a center point. But if you draw a circle in the physical world, you create a jagged, chaotic trench of rocks and sand. We can see the mechanical failure of physical geometry clearly by drawing a tangent line. A true mathematical tangent touches the curve at exactly one point. The physical line drawn in the sand touches at dozens. For Plato, this paradox had a metaphysical solution. He argued that the perfect circle exists in a separate, immutable realm of forms. The physical world we observe is a mere shadow, an imperfect imitation of that higher mathematical reality. Aristotle rejected this entirely. He identified a severe epistemological problem. If every science, geometry, kinematics, astronomy, requires its own realm of perfect forms to be true, you are forced to posit an infinite multiplicity of universes. It is massive ontological bloat. Aristotle proposed a radically different thesis. Mathematics can be exact, eternal, and universally true while being grounded entirely within the physical world. The solution is a framework of fictionalist physicalism. To replace Platonism, Aristotle had to build a system that avoided four distinct logical traps. The first puzzle is precision. If mathematical objects are grounded in physical matter, the theory must explain how we extract perfect geometric definitions from objects that are always physically flawed. The second is separability. Mathematical truths are eternal and unchanging, yet physical matter is subject to decay and destruction. The framework must reconcile the two. The third is plurality. To prove a theorem, a geometrician often needs multiple identical shapes. Platonic forms fail here because there is only one absolute form per shape. Aristotle needs to supply an infinite number of them. The fourth is non-revisionism. Any philosophical solution must be compatible with the actual language, methods, and practices of working mathematicians. Aristotle's physicalist theory survives only if he can satisfy all four of these constraints simultaneously. Aristotelian mathematics begins not with an idea, but with raw, perceptible magnitude, a physical object in the natural world. To study this object mathematically, Aristotle employs ephiresis, removal or abstraction. This is not a psychological illusion, where we simply pretend certain traits do not exist. It is a rigorous, logical operation. The mechanism that executes this operation is the qua filter. The term translates from the Greek he, meaning in the respect that, or by means of the fact that. If we study this physical object qua bronze, we intentionally restrict our investigation to its metallurgical properties. We test its density, its melting point, and its reaction to heat. But if we switch our logical restriction, we can study the exact same object qua sphere. The filter removes the physical attributes from our consideration. What remains is noetike hele, intelligible matter. It strips away the perceptible matter, isolating only the geometric extension between the limits of the object. This operates under a strict logical boundary known as qua realism. An investigator can only study an object qua a specific property if the object actually possesses that property. Through this operation, mathematical objects are not alternate dimensions or mental fictions. They are physical objects, viewed through a highly restrictive logical lens. We can now test if the qua operator resolves the four ontological crises. First, the puzzle of separability. How can a physical shape be eternal if the bronze it belongs to can be melted down and destroyed? When we apply the qua filter to study the object qua sphere, we intentionally filter out the attributes of time, generation, and destruction. Because these variables are removed from the logic, the resulting mathematical object is treated as if separated. Second, the puzzle of plurality. Complex geometric theorems require multiple versions of the exact same shape. Historical Greek proofs fundamentally relied on comparing distinct, formally identical geometric entities to function. Aristotle's solution relies on volume. The physical universe contains countless physical objects. Passing any combination of them through the qua filter yields an infinite supply of identical mathematical forms to manipulate. By isolating intelligible matter from physical matter, Aristotle solves both the existence and replication problems of mathematics, with zero reliance on a separate, mystic reality. This brings us to the puzzle of precision. This is the most difficult historical hurdle in the Aristotelian framework. Scholars still debate the exact mechanics of how Aristotle resolved the gap between imperfect physical objects and perfect mathematical definitions. The strongest resolution lies in material potentiality. A perfect mathematical line or sphere exists as a potential within the continuum of physical space. It is actualized by the geometer's precise division. By extracting that potentiality via intelligible matter, the math achieves exact precision. Finally, non-revisionism. Does this dense philosophical framework break how actual working mathematicians operate? Ancient mathematicians did not work with perfect geometric objects. They drew rough, highly imperfect diagrams on papyrus or sand and used those to calculate their theorems. For Aristotle, this practice is perfectly valid. The mathematician's rough drawing is merely a physical stand-in. By applying the qua operator, the flawed drawing represents the universal hypothesis, maintaining the logic of everyday mathematical practice. All four quadrants are resolved. Aristotle has built an epistemological framework where mathematical truths are exact, eternal, and entirely reliant on the physical universe. Because mathematical objects are derived from physical quantities, their rules inherently govern physical reality. Aristotle maps this interaction through strict deductive boundaries. A given science is autonomous, defined strictly by its genus, and the properties that belong to it per se, in virtue of itself. This rule of autonomy means a mathematician cannot use a theorem in arithmetic to prove a theorem in geometry. The properties of discrete numbers are fundamentally separate from the properties of continuous magnitude. However, these sciences do interact through a specific mechanism called subalternation. Geometry links downward to mathematical optics. Mathematical optics links downward to empirical optical phenomena. The descriptive physics relies entirely on the abstracted math to explain its own rules. In this system, mathematics is not a disconnected ideal. It is the operational code required to decipher the physical world. We can see this architecture clearly in Aristotle's meteorological investigations of the rainbow. At the bottom of the hierarchy is empirical observation. The physical fact is a rainbow observed on flat ground is never more than a semicircle. But empirical science has a fundamental limitation. Observation provides the fact that it is a semicircle, but it cannot provide the explanation why. The explanation lies in the higher, subalternate science, mathematical optics. By analyzing water droplets through the qua filter, optics uses reflection geometry to prove the arc's physical limits. The logic traces from empirical sight up to optical geometry, resting on a hypothesized mathematical postulate. For Aristotle, the path to understanding the physical world does not require escaping to a realm of perfect forms. It requires looking directly at the physical world and applying the precise, logical lens of the qua filter.